Hey everybody, welcome to a video because we're not going to be in class tomorrow. So I'm going to cover section 4.4, which is slightly out of order, but I think it will go faster than 4.3 in video form, and I can save my throat. So let's hop right into it, section 4.4, and then we'll cover 4.3 when we come back. I'm going to share my screen and then have you follow along on the, okay. Yeah, so you should follow along on your own handout. So section 4.4 is about something called L'Hopital's rule. The name is French, so it's not La Hospital, even though that's how it looks, L'Hopital's rule. And the idea is that we're applying derivatives to things that we couldn't do before. Chapter 4 is about applying derivatives. So this rule that we're going to cover, L'Hopital's rule, is a way of evaluating limits in ways that we could not do back in chapter 2. So we're going to revisit some limits from chapter 2 that we couldn't do, and many of these limits show up all over the place, in particular Calc 2. Okay, so just to motivate where this comes from, consider a limit like this. X goes to 0 of sine x over x. If you remember trying to evaluate limits from 2 chapters ago, what you say to yourself is, I'd like to plug in 0 for x, and then just get the limit. But notice you can't do that. You plug in 0 for x, you're dividing by 0, and also sine of 0 is 0. So if you plug in 0, you get 0 over 0, which, if you remember chapter 2, doesn't really tell you anything, actually. You would like to say dne, but no, actually, if you do 0 over 0, you just shrug. You can't say anything. So L'Hopital's rule now exists so that we don't have to shrug. We can say what the answer is. Okay, so here's how the rule works. It says, suppose you're trying to take the limit of a fraction. So the fraction there, just like in the example, sine x over x. You're trying to take the limit of a fraction. That limit is said to be indeterminate of type 0 over 0 if the top and bottom both go to 0. So sine x goes to 0 as x goes to 0. X goes to 0 as x goes to 0. So sine x over x has that form. And you're also said to be indeterminate of form infinity over infinity if top and bottom both blow up as x goes to wherever. So sine x over x, nothing blows up as x goes to 0, but we'll see some examples later where top and bottom both blow up instead of going to 0. So all this is saying is, if you're trying to take the limit of a fraction, and that limit is not nice in the sense of chapter 2, like you end up writing down 0 over 0 or infinity over infinity, L'Hopital's rule can now help you evaluate that limit, whereas in chapter 2 we couldn't. So L'Hopital's rule says, I don't have the rule yet, just indeterminate forms. Okay, yeah, so let's start with, so L'Hopital's rule is based on these indeterminate forms, so let's practice with those first. So here, as x goes to 0, oh, please stop. As x goes to 0, sine x goes to 0, and x goes to 0. So that limit is form 0 over 0. Okay, let's think about this. As x goes to 1, what happens to the natural log of x? As x goes to 1, what happens to x minus 1? So natural log is one of those functions you're supposed to know. So as x goes to 1, natural log of x goes to 0. And the reason is because natural log of 1 is 0. So this is like a background fact. Natural log of 1 is 0. So here, again, we have 0 over 0. As x goes to 1, natural log approaches 0. As x approaches 1, x minus 1 also goes to 0. 1 minus 1 is 0. Okay, the next one. This one, as x goes to 1, I get a 0 down below. But as x goes to 1, I don't get 0 up top. So this is like 4 over 0. I know what to do with that. That's a D&E from chapter 2. So you have to be a little careful. It's not like every limit we see now has 0 over 0 or infinity over infinity form. Okay, a couple more. Sine of pi. So this is saying as x goes to pi, what happens? So if you remember your unit circle, sine of pi is 0. If you remember your unit circle, cosine of pi is -1. So if you plug in a pi for x into the bottom, you also get 0, 1 plus -1. So far we've seen 3 examples of 0 over 0 indeterminate type. So limits we could not do back in chapter 2. Okay, this next one, as x goes to 0, the bottom is just 0 squared, which goes to 0. The top, e to the 0. E to the 0 is 1. So this is 1 minus 1 over 0. Okay, so another example of a 0 over 0 limit. Okay, one more. This one, you again have to remember what the graph of natural log looks like. Graph of natural log looks like this. So as you approach 0 from the right, you're walking in like that. As you approach 0 from the right, natural log dive bombs down to infinity. 1 over x, you have to remember what that looks like. 1 over x looks like this. So this is natural log of x. This is 1 over x. So as you march in from the right, the function blows up. So this has infinite indeterminate form. As x goes to 0 from the right, it doesn't matter left or right overall. Well, sorry, it matters in that, see how natural log, there's nothing over here, right? Nothing going on there. So I have to come in from the right just to have it make sense. Anyway, so as you approach 0, you get here a fraction that's infinity over infinity. So all of it to say, we've looked at 5 limits, 6, I don't know, I can't count. And 3 of the limits, sorry, 4 are 0 over 0. One of these limits wasn't anything indeterminate. We could do that already. And then one of them was infinity over infinity. That's the idea of an indeterminate form. Okay, so like I was saying 5 minutes ago, L'Hopital's rule exists to deal with L'Hopital's rule likes these 0 over 0, infinity over infinity. These ones that we could not do back in chapter 2. L'Hopital's rule comes in and tells you what to do. So let's get to L'Hopital's rule. It says this. It says if you're trying to take the limit of a fraction, which we were looking at on the previous page, you want the limit of a fraction as long as that fraction has type 0 over 0 or infinity over infinity, then the limit that you care about, which is this, equals this limit, where you just take derivatives of top and bottom. So it's kind of weird. It's like a quotient rule that you wish existed. Because remember back in chapter whatever it was, if you think about the derivative of a fraction, you would kind of like this rule to be true because it'd be easier than the actual quotient rule. Now, unfortunately, that's false. But L'Hopital's rule says, well, there is a context in which this kind of thing kind of happens. So here it's saying the limit of this fraction, you can just slap primes everywhere and take that limit. Now, not obvious why that's true at all, and I'm not going to prove it to you. We're just going to use it. But it's a shocking result, actually. There's no way you would think that's true unless somebody had proven it to you. So I don't know how L'Hopital came up with this. It's crazy. Okay, so now it says, hey, let's go back to the previous page and use L'Hopital's rule. Oh, and you might also ask, how is this useful? I mean, I was taking a limit of a fraction, and then I change it into limit of another fraction. Have I done anything? Have I made the problem easier? And the answer is yes, actually, sometimes. And certainly for the problems you'll do in this section. Okay, so I left a bunch of room here on this page for you to do this if you would like. Okay, let me come back up here. Now we're going to just calculate these limits using L'Hopital's rule. Excuse me, I'm trying not to cough too much. Let me clear all this out. So I want to calculate these for you and show you how to write your work. You need to write your work in such a way that you communicate that you know how L'Hopital's rule works. So I'll show that to you. So in these problems, you're going to write things like this. 0 over 0. So that's not like a funny face or something that looks, I don't know. I try to make it 0 over 0. So that limit equals something else, and it equals that because it's 0 over 0 indeterminate form. So L'Hopital's rule says, once you recognize that that has form 0 over 0, you can just take derivatives of everything you see. Derivative of sine is cos, derivative of x is 1. So if you ask, is this rule of any use? Does it actually make these limits easier to calculate? The answer is yeah, actually. In this case, notice we no longer have an x in the bottom. And that was what was stopping us before. Dividing by 0 is bad. But now Recall from chapter 2, if you can plug in 0 for x and not have something explode, you just do that. So I get cosine of 0 over 1, and you should remember from a unit circle that cosine of 0 is 1. So I just get 1 over 1, which is 1. Okay, so all of that to say, this limit in chapter 2 was a big old question mark. We had no way of dealing with that. We had no idea what was happening. But now in chapter 4 with L'Hopital's rule, we can figure out that limit in about 20 seconds. So that's pretty impressive, actually. It's a neat rule. Okay, so now let's keep going. We already said this was 0 over 0. Okay, so now let's do L'Hopital's rule. I take derivative of top and bottom. The derivative of natural log is 1 over x. The derivative of x minus 1 is just 1. So you can simplify this if you feel like, but I'm just doing that. And now if we were in chapter 2, you would just plug in 1 for x. And once again, you get an answer of 1. 1 divided by 1 is 1. Okay, so we've gotten 2 1s. That's just a fluke, you know. But again, chapter 2 says what? Chapter 2 says, I can't handle that. Now we can handle it. This one we already talked about was D and E. We don't need anything for that. That's chapter 2. Okay. All right, I apologize. I may cut this short so you don't have to listen to me cough. Okay, we already said that was 0 over 0. So now L'Hopital's rule says we can take derivative of top and bottom. So derivative of 1 is 0. Derivative of cos x is negative sine. Okay, so let's think about this. Let's do some back of the envelope calculation. Cosine of pi is negative 1. Let's imagine plugging in pi for x and see what happens. Negative sine of pi. So sine of pi, that's sine of 180, that's 0. So we have now a limit where if we plug pi into the bottom, we still get 0. If we plug pi into the top, though, we don't get 0 anymore. We get negative 1. So this is, put this in quotes, this is like saying negative 1 over 0. And we know that doesn't exist. There's no ambiguity there. It's not indeterminate. So we actually did learn something by doing this. So originally we couldn't say D and E. We didn't know. But L'Hopital's rule let us write down a limit that was equivalent where we did know. Okay. This one we said was 0 over 0. So let's take derivative of top and bottom, as the rule says we can. Derivative of x squared is 2x. Derivative of e to the x is e to the x. Derivative of negative x is minus 1. And then derivative of just that free-floating negative 1 is 0. So now we have this limit. As x goes to 0, this new fraction, which is smaller than the old one. But now notice, if we plug in 0 for x, like that, so e to the 0 is 1, we still get 0 over 0. So in this case, L'Hopital's rule did not give us a limit where we could immediately plug in the value. So you could say, well, that was useless. That didn't get us anywhere. And I would say, I mean, maybe, but also notice this limit here, this is smaller, simpler than the original one. No more x squared, no more free-floating x, that minus x. And by the way, L'Hopital's rule, there's no rule against using it again. So this limit here also has form 0 over 0. And whenever you have 0 over 0, you can use L'Hopital's rule and see what happens. So let's take derivatives again. Like that. So here, the original limit was 0 over 0. So we took derivatives of top and bottom, like L'Hopital's rule said we could. And then the resulting limit was also 0 over 0. So you can just take derivatives again. There's no limit on how many times you can use L'Hopital's rule on the same problem, as long as it keeps being 0 over 0 or infinity over infinity. And now finally we can plug in 0 for x and we get an answer of a half. Let me just again emphasize the way I'm writing my work is the way you should do it. So you're communicating why you can use L'Hopital's rule by putting that 0 over the equal sign. You can, of course, write in English by L'Hopital's rule because of 0 over 0. Like you could write all that if you wanted to, but this is communicating the same thing with much less writing. Okay, finally, this one here, we said this was infinity over infinity. So L'Hopital's rule comes in and says, okay, you can take a derivative of the top. You can take the derivative of the bottom. So now let me do some scratch work. Derivative of 1 over x. We've done this plenty of times, but let me just remind you, we're just going to use the power rule on that. Like that. Bring the negative 1 down, knock the power down by 1. And then if you like, it's negative 1 over x squared. And put negative 1 over x squared here. And now you could say, wow, that looks way worse than the original. The original had a natural log, which maybe wasn't nice, but now I got fractions inside fractions. How gross is that? And, you know, fair enough. I'm not going to tell you how to feel. But notice if we simplify this, so let's do some simplification. So 1 over x over negative 1 over x squared. We can do the fraction division. That's 1 over x times negative. You multiply by the reciprocal. So we have x squared over x, basically. X times x over x. So up top, one of those x's cancels, and we get just negative x. Like this. So if you're willing to simplify the fractions, then you get something much nicer. The original problem was natural log over a fraction. How gross is that? But we got now a limit here, much nicer. Just limit basically of x, negative x. And now if you plug in 0 for x, you've gotten to a place where you're not dividing by 0 or whatever. You can now say the answer is 0, negative 0. Okay, so there's 5 examples of using L'Hopital's rule. We did 4 examples of 0 over 0. We did 1 example of infinity over infinity. That's how the rule works. It's worth pointing out real quick. So limit x goes to 0. So consider something like this. There's 1 or 2 like that in the homework. X times natural log of x. Find that limit. If I ask you to find that in the homework, one reaction could be, I don't know how to do that. L'Hopital's rule is for taking the limits of fractions. So if you give me something that's not a fraction, what's the deal with that? What am I supposed to do with that? Products are not fractions. So that's a reasonable reaction, but my response to you would be, well, products can be fractions if you want to think of them that way. So dividing by 1 over x, as ugly as that looks, that's the same thing as multiplying by x. Okay, like dividing by 1/2 is the same thing as multiplying by 2. So this limit here is the same as the limit we did on the previous page. You just have to take that intermediate step of recasting that product as a fraction. Okay. So now I have several exercises here. If we were in class, we'd have plenty of time to do them. Of course, we're not in class, so we're not going to do them. But you should try doing several of these on your own. There are answers somewhere in here with the solutions typed out. So with the explanations there. So if I were you, this video is only 20 minutes long or something. I would try at least the first, I mean, you should try all of them ideally, but try the first like 5 or 6 maybe. So this one here is similar to that double step that we did with the e to the x problem. So I would try the first 6. If you're ambitious, try some more and see how far you get and check your work against the answers. Okay, I apologize for my coughing in your ear. Hopefully that wasn't too bad. And hopefully this was understandable. If not, you shoot me an email. We talk about it next week. All right, have a good weekend.